Modern diesel engines are cleaner and more efficient than ever before. But new, more stringent emission standards are coming in 2024 and 2027 to lower CO2 and NOx emissions even further. NOx will be reduced by up to 90%, CO2 will be reduced by 25 to 30%, and a new low-load emission standard and in-use specifications will be required. Modern after-treatment systems feature a selective catalytic reduction, or SCR, catalyst that manages the amount of NOx leaving the vehicle's tailpipe. The high NOx conversion temperature range for this SCR catalyst is between 250 and 400 degrees Celsius. Unfortunately, engines spend a lot of time operating at low loads, preventing the catalyst from reaching peak conversion temperature. Eaton diesel cylinder deactivation, or CDA, is a proven solution to increase the exhaust temperature to quickly heat up the SCR catalyst to the peak conversion zone while reducing fuel consumption, or CO2, at the same time. Eaton cylinder deactivation can be applied to all medium and heavy-duty engine types: double overhead cam, single overhead cam, and cam in block. Now let's take a look at how the system works using today's after-treatment system. In this engine, all 6 cylinders are active, meaning they're operating normally. Air and fuel are entering the cylinder and being compressed to create exhaust, which is being represented by the NOx particles in red and the CO2 particles in blue. Let's focus on cylinders 3 and 4. During low-load operation, typically below 3 bar BMEP, diesel engines suffer from low exhaust temperatures, as shown in the dark blue area on the graph. Deactivating half of the cylinders at low loads increases the exhaust temperatures into the peak efficiency zone. Let's illustrate this operation by showing all 6 cylinders operating normally. The exhaust temperature is cold. As we deactivate half of the cylinders, cylinders 4 through 6, the exhaust temperature in the active cylinders increases by 100 to 200 degrees Celsius because they are working harder. These active cylinders are producing more NOx, but it's significantly less than if all 6 cylinders were firing. CO2 is also reduced. Notice that the exhaust flow rate is cut in half. Because the after-treatment system is now operating in the peak efficiency zone, we can switch back to all 6 cylinders firing and the exhaust flow rate returns to normal. This would be above 3 bar BMEP, since the best fuel savings mode below 3 bar is still CDA. Now let's add a current after-treatment system to the engine. The urea injector is upstream of a diesel oxidation catalyst, a diesel particulate filter, an SCR catalyst, and an ammonia slip catalyst. All 6 cylinders are operating as normal. NOx and CO2 particles are flowing through the system, and the exhaust temperature is cool. If we deactivate cylinders 4 through 6, you can see that the exhaust temperature increases. The exhaust flow is reduced, and NOx and CO2 are decreased. This setup could be used to achieve 2024 emissions targets. In the future, a light-off selective catalytic reduction, or a low SCR catalyst, will likely need to be placed very close to the engine to improve NOx conversion efficiency. This placement allows the low SCR to heat up more quickly in low-load conditions. Combining cylinder deactivation with the close-coupled SCR after-treatment system is key to achieving the 2027 mandate of less than 0.02 grams per horsepower-hour of NOx. An additional benefit of CDA is the ability to clean sulfur from the SCR. Cylinder deactivation can heat the exhaust temperature to above 500 degrees Celsius, which is enough to remove the sulfur from the low SCR, eliminating the need for an additional diesel oxidation catalyst or fuel injector upstream to desulfate the catalyst. In summary, we believe a systems approach using cylinder deactivation and a close-coupled after-treatment system can simultaneously reduce NOx and CO2 and achieve future emission standards for medium and heavy-duty diesel engines.